All right, so I have started the recording. Fine. So let me quickly take you guys to the syllabus copy. So we are left with 3.4, which is part of IPv6. Okay, which covers completely NRC, and from NCore we have 1.4, the SD WAN and the traditional WAN. Okay, so what I'm going to do is, first I'll take up IPv6, and then we'll go towards SD WAN. Okay, so basically this will be the last two topics from CCNP. All right, so what do we understand by IP6? Why do we need this? What's the importance of having the version 6? Okay, what is the header length of IPv6? So these are some questions which basically are asked in the interview. Okay, so if you just compare first IPv6 with respective to IPv4, so let me tell you, IPv4, which consists of 32-bit. Okay, if you just get it, okay, 1 second. So if you count the total number of IPv4, you have close to 4.3 billion. Okay, 1 second. So I guess some issue with the pointer. Give me 1 second. Okay. Okay, so let me use this. All right, so let me use this. Okay, this pointer. So if you calculate the IPv4 total number of IPv4 possible, so this would be the count, which comes up to 4.3 billion. Okay, now the strange thing is the whole population of the world is close to 7 billion, or I can say approximately 8 billion. Okay, even if one individual right now has at least two devices, that means he's using two IP addresses, so this would have been exhausted by now. Agree, this would have been exhausted by now, but we are still making use of IPv4. If you technically speak, almost everyone are still using IPv4, even though we have the next technology IPv6 with us. Okay, the only reason why we are surviving with IPv4 is because we are using NAT. Okay, especially so if you know, there are three flavors of NAT. One is called as dynamic NAT, static NAT, and port address translation. So especially this extension of NAT is uh, helping us to still be in IPv4 address, because you know that in the case of PAT, one single public IP can accumulate multiple private IPs basis on port number. If I have 1.1, I can map that with a port number. If I have 1.2 or 1. Let's say 1.1, I can map it with another port number. So basically same private IP, same public IP, but depending upon the services or port number, we can keep a separate identification for each of the traffic. Might be the first traffic is for WhatsApp, might be the second traffic is for Skype, right? So PAT is helping us to achieve this kind of scenarios, or I can still say, even though we have crossed the total number of IPv4, still we are surviving with the help of version 4. But as a plan B, it's always good to have the next technology being tested up and being getting used up, right? So that one fine day, if we are all done with the natting, if we are all done and we just need something better, we have the next technology with us. Okay, so in today's class we will check about IPv6 and I will try to compare it with the version 4. Okay, so if I say IPv6 versus IPv4, the first simplest difference should be the size of these IP addresses. Okay, so basically if you talk from the header point of view, this consists of 32 bits, whereas IPv6 consists of 128 bits. Okay, in the case of IPv4, we need NAT. Let's say PAT or NAT or PAT. Okay, the dynamic NAT, the static NAT. You know what is static NAT. Static NAT is one flavor of NAT which maps private to public one-to-one basis. Okay, and I cannot go and make use of static IPv4 NAT uh, always. The reason is, if that would be the situation, then the IPs would have been exhausted by now. Okay, so we prefer having NAT and PAT to give more life to the IPv4. But for IPv6, we don't need the concept of NAT at all. There is no NAT, because if you consider IPv4 and IPv6, I can say that 50 times, okay, 50 times of IPv4 is your total number of IPv6. So why do you think we need a concept of NAT in case of IPv6? Because we know we're still surviving, 7.8 billions of the world's population still surviving on IPv4, okay, due to the NAT and all those things. But if I say IPv6 is much more than IPv4, 50 times, okay, so might be for next 20, 30, 40 years, you don't have to have the concept of NAT in IPv6. Just even the static kind of mapping, that is one-to-one mapping, that is also more than enough. Okay, the third difference here is the mode of communication. So we all know that the three mode of communications are unicast, broadcast and multicast. Okay, whereas here in the case of IPv6, we don't have concept of broadcast. Okay, there is no broadcast. It's simple unicast. We got multicast for the routing protocols, and there is something called as anycast. Okay, now anycast and broadcast are not the two same things. Okay, you know that broadcast is flooding, but anycast is not flooding. It's a mechanism in IPv6, I can say intelligence mechanism, where let's say I had a Fi load balancer. Okay, and behind this load balancer I had some web servers. I had A, B and C. Now in a normal situation, in a case of IPv4, we give a dedicated IP to these 1.1, 1.2, 1.3. Now what happens is the load balancer keeps a table where it is gonna say that this connection will go to the first, the second connection will go to the second, and third connection will go to third. If let's say one device goes down, now there will be some MAC address changes or fluctuation, or the new entry of a MAC address, right? But in the case of anycast, I'm gonna give the same IP address to all the three servers, 1.1, 1.2, 1.1 once again. Over here, I'm gonna define that it's a part of anycast. Now what happens is Fi is just gonna push it to 1.1, and this anycast, they take care of the servers. Whoever is active and running up, they will be responding to those traffic. Okay, so that's a difference, few of the difference between IPv6 and IPv4. There are also other things here, okay, which I'll tell you as we proceed. So first, let's understand the IPv6 format, okay, or the packet format. If I write IPv4 first, okay, so we all know that it's a 32-bit, and the packet is divided into 8 equal sorry, not 8, 4 equal components or content, or which I can call also as octets. So let's say this is a octet, this is another octet, there's another octet here, okay, and same thing goes here. Now each octet consists of 8 bits, 8 bit, 8 bit, 8 bit, and 8 bit, okay. So altogether they form a 32-bit. Fine. Now these bits can be written in decimal format or binary format as well. So if I happen to write, I can write it in this format. So 4 and 4. So altogether 8 bits. Okay. And if you just change this value, let's say if I happen to write something like this way, then starts this, right? So just trying to add the next value. Okay. So I can say that the minimum value starts from 0 and the maximum goes up to 255. Okay, if you happen to get some time, you can just see what is the topmost bits value. So this results in 255 decimal format. How do I calculate? I go with 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 4, 5, 6, and 7. So the end result is 255. Okay, so I can say that my IP address, the shortest IP address could be this. If I try to write the maximum or the last IP address, then that's gonna be 255, 255, 255, and 255. This is something which we know from CCNA topics. We know that this is how IP4 is written, and we have number of ways to reserve it, unless or until I don't want to use class 24 for just a team size of 5 people. We know we can go with the VLSM subnetting, or we can go the fixed one or the variable, right? So we have different approaches to reserve the IPs. We have the classes of IPs, different classes, right? So we are aware with IPv4, but what about IPv6? What does IPv6 consist of? So basically it's a 128-bit. So things will be little complicated. Okay, so if I draw the header for this, okay, now we are gonna have 8 equal components. Okay, so it would be 8 into 1 2 3 4, 4 into 8. Okay, so we need to have total of 128 bit. So we are gonna calculate what is that value. Okay, so let's say if I write it in this way, okay, 1 2 3 4 5 6 7 8. So they are not what I've done is not equally in a width, but just take it as a equal width. Okay, so let me say that this act as first octet, this is second, third, fourth, fifth, sixth, seventh, and eighth octet. Okay, each one are gonna carry 8 bits. Okay, so totally 8 bits of the concept. Now in the case of IPv6, we divide the entire block into 2 prefixes. Now we don't have a concept of class A, class B, class D. We don't have this. Okay, Neither we have a concept of class 24, class 16 or class 8. We don't have this. This is a IPv4 concept. In the case of IPv6, we are straight away gonna divide into two equal components. Okay, that's going to be 64-bit on this side and 64-bit on this side. That's how we are gonna represent IPv6. Only 2 bits. Okay. Now let's say if I write a dummy IPv6 value here, so let's say 2001 0db8, some random value. Okay, 1 2 3 4 0 0 0 0 0 0 and 3c4d. So basically they are 4 bits. Okay. Now let's say if I just bring this value 2001, and if I wanna understand from one single octet point of view, I can say that each portion, okay, each portion is gonna contain 16 bits. That means if I convert 2001 to bits, then I must have 16 bits with me. Okay, now they are 4 plus 4 8, and another 4 12, and then last 4. So total this kind of 16-bit. I'm talking about only one portion. Okay, we call this as portion. One portion equals to 16 bits. Now 8 portions, 1 2 3 4 5 6 7 8. Okay, so 8 portion equals to 128 bits. Okay, so if you calculate 8 into 16, you're gonna get 128 bits. Okay, so 16 16 16 16 16 16 16 and the last 16, so total 8 times it's gonna be 128 bits. So you just see the difference of v4 and v6. In v4 it was 8 bit, over in IPv6 we have 16 bit. Okay, so each digit, so if I say this is first digit, this is second digit, this is third digit, and this is fourth digit. Now each digit act as 4 bits. Okay, so if you have 4 digit, it's gonna be 16 bits, right? So basically you have 4 digit equivalents to 16 bit, and we know the cross connection now in case if we need to convert this. Okay, so yes, it's called as portions, 8 portions. Each portion consists of 16 bits. Okay, so 16 into 8, 128 bit together, v6 versions. Each digit, now let's say if I have written over here, so I can say that this is a digit, this act as another digit, this act as one more. So each digit will have 4 bit. Okay, so that's from the IPv6 packet structure. Now let's talk about IPv6 addressing. Okay, now what I'm going to do is I'm gonna write one lengthy IPv6, and we are gonna see if there is a mechanism to shorten that IPv6, or we need to remember the complete portions, total 16-bit or whatever 8 portions, do we have to remember them? Okay, so let's say if I write the whole content of IPv6, so I have first portion, second, third, fourth, fifth, sixth, seventh, and eighth. Okay, so I'm going to write 2001 0db8 0 0 0 0 0 0 1 2 3 4 0 0 0 0 0 0 3c4d. I know it looks little complicated to remember, but let's take this as an example. Okay, and I would like to say IPv6 are easy to memorize, but you need to know the shortcut for doing that. Okay, So in this case, when it's 2001, I don't have any way to shorten them up. Okay, I have to write as it is. 0dBd, still no changes. I have to write as 0dB8. But when they are all zeros, I can just write them as a single zero. Okay. Yes, don't forget including these colons. Okay. Similar way, this gets shortened to a single zeros. I have 1, 2, 3, 4. So there's no more shortening happening here. So I have to write 1, 2, 3, 4. This goes and just becomes a single zero. Same goes with this single zero. This goes with 3C4D. Okay. Now this is IPv6 structure. But yes, we can still go one step further. Okay. We can still go and shorten it up. So let's say I have 2001 0dB8. Now these two can be written as a single zero. Okay. And then I can bring 1, 2, 3, 4. Now if you're thinking, because I did on the first side, if you're thinking that second side will also be shortened up, then you're wrong. We are not going to shorten them up anymore. Okay. So they are gonna be the way it has to be. Okay. Then 3C4D. Now the whole thing over here can be just written at this columns. Okay. Now let me write the final version. 0dB8 1 2 3 4 0 0 3C4D. This becomes the final shortened IPv6. Okay. So what does this gonna represent? It's gonna represent that there are 8 zeros. Okay. Now if you're wondering why didn't we do uh, why didn't we shorten up this two things, we could also have written it in this way, right? So yes, we can do that. Okay, so let me say, if I have to write the final version, so this becomes the final version. Okay, this is the final version, or the simplest or the shortest that I can do it for this kind of IPv6. Now why I am telling this is, this is not this don't have to be right in every cases. Okay, for example, these zeros I purposefully have not shortened up in the first case because I wanted to tell you if the scenarios were little different. Okay, so something like 2001 0D38 000 000 then you have 1 2 3 4. Okay, and then you have another 000, and then finally give me a second. Okay, so finally you have 3C4D. Okay, now if you observe, you have three portions acting as zeros, and then you have one portion. In this case, we cannot go with this kind of shortening. Okay, the reason is it can lead to confusion. So you can say you have one portion of zeros here followed by some digit in between, and then you have three zeros or three portions of zeros, or that can also make look like three portion of zeros, then you have the digits, and then you have one portion of zero. Now this is a different thing. So say for example, if I say 1.0.1.1 is something else, and 1.1.0.1, this is something else, right? So when you have imbalance, that means you have 3 on one side then followed by some numbers and then zeros. In that scenario, we cannot minimize the second bit or the second half portion. So this cannot be minimized. Okay, but since here they were equal, two on left side and the rest two on the right side, so we could easily shorten it up in this way. Okay, so always remember, whenever you have this zeros, if this whole things were complete zero, we could still be going to very shortest format. Okay, just a colon. But since we have in between something else, we can still go with two colons, 1 2 3 4, and again two colons. That's possible. Okay, if they were all zeros, I could have gone with two colons. But if they were three on one side or and one on the other side, in that scenario it's not going to happen. Okay, because when we are expanding it, we can take it either in this way or we can take it in this way. We never know what would be the end result, so we will not do any shortening when the zeros are not properly balanced. Okay, now let's talk about IPv6 address type, the different IPv6 address types. So I told you the mode of communication, right? So we have unicast, we got multicast, and we have anycast, the three different types. We don't have broadcast in IPv6. Okay, so under unicast we have three flavors. Okay, so I can say one of it is called as global unicast, and global unicast act as your public IP, the normal IPv4 public IP. So I'm going to write it that way. The second flavor here is called as unique local. Okay, which act as your private IPs of your IPv4. If you know IPv4, we have IPv4, we have public and private. Okay, so we also know there is a RFC code 1918 which defines the classes and the private ranges. Okay, so in the case of IPv6, we have unicast, global unicast, which act as public, and unique local, which act as private. There is third flavor here, which is called as link local. Link local is like your loopback address. Okay, they are automatically created on any interface which is capable of IPv6. Okay, that means if your routers or if your, let's say your CMD, okay, if let's say you are making use of these modems which supports IPv6, then basically you will also see the IPv6 automatically getting constructed. Okay, without you doing something. So if I do IPv config, so you can see there are so many IPv6 because my modem is supporting IPv6 routing. And this way I get this. These are called as link local IPv6 address. They are enabled by itself. Okay, if your interface, if your routing is capable of handling IPv6, they will be automatically getting created. These are all link local. They are non-routables. Okay, they are not used as public or private. They are just getting associated, or they just get generated by itself on a IPv6 capable interfaces. Okay, so let's see about these two first. That is about public and private. Okay, so as I told you, this is your public in nature. How are we going to uh, recognize if it is a public or private? Because when we have IPv4, we have certain dedicated groups for for private. Okay, so in the case of 10 series we have that /8, in the 172 series we have that 16, in the 192 168 dot series we have the we have for class 24. Okay, so we can say by seeing on these starting octet, or or if you talk from the class point of view, A, B, C, D, we still have that range where we can say that this belongs to this group. But in the case of global unicast, or in the case of IPv6, since we don't have all these concepts, we have a dedicated numbers which tells whether it's a public or private. So if you see any IPv6 which starts with 2, okay, now that's part of public. Or if anything starts with 300, which has still not come up, okay, you will still see IPv6 getting used or getting started up with number 2. There are pretty much more number of years to come. When these series are exhausted, then we start seeing 3. Okay, so we have IPs, public IPv6 IPs, which starts with 2 or 3. Okay, and they are gonna have this kind of subnet masks, the /3 kind of thing. Okay, now regarding unique local, it's a private and it's a routable capable. Even this is capable of routing. That's important to know. Okay, routable. What else, or how does this IPs look like? So your IPs here will either start with FC or it will start with FD. Okay, so depending upon this FC or FD, you can recognize whether it's a private IP or it's a public IP. Basically, who are giving these IPs? It's your online entity called as INA. Okay, the one who was also giving us IPv4 is the same online entity which is giving IPv6 reservation also. Link local, as I told you, they are automatically created and they are non-routable. So the moment I say non-routable, they are of no use to us. Okay, they just do not forward any kind of packet. They just get associated with those interfaces which is capable of handling IPv6. Okay, that's the only thing. What about multicast now? So in the case of multicast, the behavior is very similar. It's between group of host and client, or the listeners who are gonna get those or receive those multicast packet. Okay, so in the case of IPv6, we had the complete 224 reserved for multicast, right? So in the case of IPv6, we have this reserved for IPv6 multicast. Okay, so if when you see the OSPF uh, OSPF v3 or the IPv6 version of OSPF, you will see the multicast IP will be listening or enabled on this IP address. Okay, or EIGRP, or if you talk for BGP, so any protocol which is capable of running over on IPv6, you will see the multicast address will start from FF and then followed by whatever it is. Okay, so this is multicast in nature. I already told you in the case of IPv6, we have something called as Unicast. It is similar to multicast, but not at all similar to broadcast of IPv4, because in IPv4, broadcast is nothing but flooding, right? Over here in IPv6, we don't have flooding. It's a different concept now. Unicast is a different concept. Okay, it's basically to identify multiple interface and send to only one, whichever is gonna find it first. Okay, say for example, I have a client here. Client is typing http.google.com. Now this request is taken to the Google server or the Google data center, and they have the Nexus boxes, Cisco boxes, firewalls, and finally they land up on the F5 load balancer. The load balancer is connected to multiple web servers. Okay, so these servers are where the actual Google is hosted. So your Google pages are hosted on this web servers. And what is F5 doing is, F5 is uh, load sharing the traffic, because traffic can come from anywhere. This is internet, so this is there could be traffic coming from various people. Okay, so F5 is accordingly distributing the traffic one after one. So the first TCP connection, the second, the third, then fourth, the fifth, sixth. Okay. In the case of IPv4, what we do is we set the private network. We set 1.1 here. Let's say 192.168.1.1, 192.168.1.2, 192.168.1.3. Now, problem with this is if one goes down, okay, the fi will make some, or it will take some time to understand if 1.1 is up or dead. There will be keep alive, there will be algorithms or everything set up, but still there will be a flap happening. Okay, there will be flap happening. The health counter will change in the inside the fi, saying that 1.1 is down, don't send any further connection. So there will be some kind of disturbance happening, right? So in the case of IPv6, what we do is we set Anycast IPv6. Now in the case of Anycast, we don't have to make use of different IPs. Okay, let's say I am making use of uh, a Anycast properties. Okay, so I'm gonna say that my IPs, I don't have to define any IPs here. So let's say I have my switch here, and switch is connecting to 3 devices. So over here, I'm gonna configure Anycast. So what Anycast does is it's gonna keep polling of all the 3 web server. Traffic will be load share one after one. If one goes down, then basically that is not gonna send any response to the switch, right? So basically switch is also not gonna respond or send any new packets to it. Okay, so whoever is sending the request to the switch is going to forward the packet to only those servers. Okay, so in this way there will be no fluctuation happening in terms of MAC address table, or the traffic which you're sharing. There's no chance that they are getting dropped. Okay, so everything will be taken care from the switch end point of view. So how do we configure this kind of boxes? It's very simple. Let's say if I have one of the router with me and I have router 3, okay, a straight to straight or a point to point connection. So let me configure a direct interface to interface connection, and we can just give a ping here. So this is router 3, okay, and on router 3 I'm gonna go to the interface 0/0. Now this is IPv6, okay. So usually we used to write IP address, but now since it's IPv6, I'm gonna say IPv6 address, and let's go with 2001. Now 2001, the moment you see this is an example for global unicast, because global starts from 200 or 300. If I would have written something like F00, now that would have been the private network. Okay, but it's fine, we can go and try with 2001. Okay, we can give some IP address /64. Okay, so we know that the first 64 is being dedicated for global prefix. Okay, might be I missed that part, let me write it here. So in the case of IPv6, if I just divide it, so let's say this is the 64 bit and this is 64 bit. Okay, so the first 64 bit is called as global prefix. Okay, and the second 64 bit or the second half is called as interface prefix. Okay, so accordingly we are gonna write this. So this IP act as my global prefix, and then I'm gonna call it as 64/64 interface prefix. Okay, and let me put no shutdown, which is a interface command. Sorry, not shutdown, no shutdown. Okay, let me open up the second box, which is R1. So let me call it as host name as R, what is it, R1. Okay, interface E0/0. Let's say IP address, but you know that IP address is for IPv4 address. So we are gonna say IPv6 address 2001.12.12.2/64. No shutdown. Okay, so if I open up these two, you can see this is dot 1 and this is dot 2. Okay, so how do I see the interface configuration? So IP int brief. So you don't have anything shown up. Okay, show IPv6 interface brief, and there you go. So the table also gets changed. Okay, so you're not gonna make use of show IP int brief now. It's not gonna show you any result. The command would be show IPv6 interface brief. So it says the interface is up and up. Okay, now you see this, there is something getting created. We know that, we are aware that we created this, but now what is this? This is IPv6 capable, and we know that whenever there is a IPv capable, the link local will get created by itself. And how did I come to know? The starting 2 bits. So you can see that starting 2 digits, technically it's called digits. Okay, FE stands for the link local. So whenever you have this uh, IPv6 capable, you will see this FE kind of address coming up. So you can ignore them, they are non-routable. Okay, so this is the most important thing now. Now how do I initiate a ping? I can just go with ping statement. Okay, so there is no variant of ping for v4 and v6 separately. So that's going to be a generic command, ping. Okay, now let's say I want to ping the second interface. So I can take this up, and there you go. So you have your packets, or you can ping them. Okay, so they are successful. If I go with repeat of 10 counts, so you can easily ping them. So this is how we configure IPv6 on the interface. Okay, now this was a public IP which started with 2001. If you wanted to go with private range, you can still go and do that. If you go to let's say interface E0/0, if you say IP address of FC00111111, okay, /64 on one side, let's copy this and put up on the second side. Let me change it to 2. Okay, now the interesting thing is, in the case of IPv4, the moment you add the second address, what happens to the first one? It gets replaced. So say for example, do show IP int brief. So you have some free interface. So let's do some testing here. Okay, so let me go to that. If I add a IP address called as 1.1.1, okay, okay, now let's see the running configuration here. So we have one IP address. Let's say I change that IP address to a different IP address, 2.2.2.2, and let's once again see the running configuration. my previous IP has been wiped and the new IP has been come up, right? If I just change similar way to another IP, let's go with 3.3. So now you see you have one more IP. But in the case of IPv6, let me show you what is gonna happen. You can configure multiple addresses and they are not gonna overwrite the previous one. So you can have multiple networks in one single interface. Now, how is this helping us? Okay, say for example, you have a device. Okay, let's say you got a router with only four interface, 1, 2, 3 and 4. In the case of IPv4, I would say that if I have only four interface, then I can only support four networks, right? Might be this is going to support the server team, this is to the sales team, IT team, marketing team. Now let's say there were more number of teams. You had HR team, you had a CEO team, you had a guest team. Now this doesn't going to support in the case of IPv4. So you would have and ended up with having a router which has at least 8 port. Agree, you're gonna invest more money or you need 16 port, right? So that's the solution here, because here each network is gonna respond or correspond to one single networks, right? But in the case of IPv6, if you have four interfaces, each network can have multiple network. Now one network can be for sales, the second one to the HR. So basically I can say that the cost expense is getting reduced in the case of IPv6. Okay, you have less number of interface, that is also fine because it's gonna have multiple interface configured under one single interface. Okay, so that's why you see here when I added up the second IP, it actually didn't replace it, but instead it just created another new entry. Okay, so let's copy this whole thing and let me put up here. So this is 0/0. I'm gonna make it as 2, otherwise it will give me error called as duplicate IP. So that is what happened. So I'll delete one of them. Okay, now let's ping over here. Now I'm trying to ping private to private. Okay, and there we go. So this is how we configure IPv6 on interface. The same process applies for routing protocol also. Okay, we can make use of the same configuration or the same concept in the case of EIGRP, OSPF and BGP. I'll give you one simple best example. Okay, so in the case of uh, let's say in the case of static IP. Okay, so in the case of static IP, if I say uh, I'm over here source and I'm gonna ping something which is behind this router. So let's talk about loop back or kind of something. Okay, so let's say if on the back end, okay, so let's say I have my public IP between the two routers and the loop back are on a private network. Okay, so this is my loop back and I have a loop back here as well. So I'm gonna show you a simple way to write a static route. Okay, so I go and say IPv6 route, what is the private IP or what is the loopback address? So let's say it's F00, it is 22.22.22. Which network is it falling under? Okay, so if it is a network, then you will define network. If it was a single loopback, you're gonna define a single loopback. If it is a network, you're gonna say it's a part of the whole 64 network. Okay, What is the next hop gateway? So if I do a question mark, you will see it's all about next hop. So we can say that it's 201 12 12 12 and whatever IP you wanna support it. Okay, so now why it is not letting me to do is because I have made use of these IPs as my point to point connection. Okay, so that's why it's saying that it's your directly connected connection. So why are you preferring that? So we can go with something else. So instead of 2, if I give 5, so that's works. Okay, because 2 is my directly connected itself. So I made use of something else and it works fine. So command is same. The command and the meaning of each component of the static route is same. Okay, it's only the IP address that you have to change accordingly. Same thing goes with the default routing. You are gonna define your IPv6 something like this, IPv6. Okay, IPv6 route. If you do a question mark, you can define your IPv6 prefix. Since it's a default gateway, how do we define a default gateway? We say all zeros. We go and say, okay, and then we define the next hop. It's like 192.168.1.1. Now the same thing, if I have to write it in terms of IPv6, now this becomes something like this. Okay, something like this. This act as a default gateway, all the networks. Okay, now interesting thing is regarding routing protocols. We can make use of IPv6 in the case of routing protocol as well. Okay, let me show you some scenario. Let's say, I have R1 as a router. I have R2. Okay, I have my host machine and I got another host machine. Okay, let's say this is a part of area 0. Fine, and we have this acting as part area 10. Let's define some private ranges here. So we have FC00 11 11 11 dot 164, and on this side I have FC00 22 22 22 and 2. Okay, so basically I want to ping from this to this. So basically I have area 10 and area 9, and in between I can say that I got 2001 12 12 12 164, and over here it's 2. Okay, so we are gonna configure OSPF v3. v3 resembles for IPv6. Okay, we know the concept for OSPF version or IPv4 version. I would have gone between this two router. I would have written router OSPF process ID network. I would have said that this IP belongs to area 0, this belongs to area 10, but now this is IPv6. So we are gonna see how does or what is the changes when we have IPv6. Okay, so to do that I need two routers. So I can say that I have these two routers which can be configured for OSPF. Okay, and for a loopback I can make use of loopback 1 and loopback, and then finally we can run a quick ping test. Okay, so let's first configure the interface, which I guess I have done already, the interface configuration. Let me quickly check. So I want to check it for 0/0, right? So on the interface, let's give the public IP. The interface is public IP. So I have dot 2 here, so that will work, that will be okay for me to use. Okay, I don't need this under this because that will be part of my loopback, so I will delete this one. Okay, this I showed you to show that the interfaces will support multiple addresses. Let me do a no. Okay, so one single IP dot 2. So on the other side I need again just a single IP and nothing else. I'm gonna say no to this line. Okay, dot 1 and dot 2. So first see the reachability, if we have the reachability. Do ping dot 1. Yes, we have the reachability. Okay, let's configure loopback now. Let's say loopback 1, the IP address is that which we just deleted. Okay, the private range. So we can give this IP. Okay, so it becomes IPv6 address, okay, /64, no shut. The same command I'll also do it on the second router with dot 2 interface. So let's say dot 2. Okay, let me quick check this. I have dot 2 here. And I have dot 1 now. Okay, am I able to ping this? Give a check. Sorry, it's dot 2. So basically it will not work because we don't have a routing protocol between the two routers. Okay, so we don't have a routing protocol, that's a default behavior. So between this we have a direct connectivity, but the network behind them, they don't have any way to reach one to other one. So we are gonna enable either static route or default gateway or any dynamic routing protocol. So let's give a try with dynamic routing protocol. Okay, so I'll go to my first router. I'm gonna say router, okay, OSPF. So if I do router OSPF, the command is for IPv4 version. Okay, this is not for IPv6. For IPv6 we have something called as IPv6 router OSPF and process ID. Okay, now in the case of IPv6, remember the IPv6 routing will be not by default enabled. You have to enable IPv6 routing. Okay, very important command, and that command is something called as unicast routing. If you don't enable this unicast routing, you get this kind of error saying that IPv6 is not being enabled. So let's enable this IPv6. Okay, let's say IP unicast. Okay, IPv6 unicast routing. Okay, so once I enable this, now my OSPF command will work fine. Okay, so basically what I did is I enabled IPv6 routing here, which was not enabled by default. I configured OSPF process. It says that it automatically took the, okay, it has not taken the router ID. So we are gonna fix that. Okay, so it's that it says that process IPv6 could not pick a router ID. Please configure manually. So we will do that. Okay, so why do you think we got this error? Don't you think we have the physical IP? Don't you think we have the loopback IP, which should have automatically created router ID? Agree? Which is what we learned in the case of OSPF. In the case of OSPF, router ID generates in three ways: either manual, or so the second case was loopback, and the third one was physical. But in this scenario, you see it gave me a very big warning message or an error message that router ID was not found. So basically OSPF process will not generate, and if OSPF process will not generate, there is no way the hello packet will be going out of this device. But why do you think it happened? It should have taken up one of the link, right? The reason is router ID, either it's a v4 or v6, doesn't matter, they are always IPv4 format. Okay, even in the case of v6, we are gonna manually take router ID in the IPv4 format. Okay, in case you had a loop back which was in v4 format, or you had a physical interface in v4, then that would have been automatically taken as a loop as a router ID for this v6. But since we don't have that, okay, we configured only on interface and loopback, and both we took the v6. We don't have v4 in our router. That's why my OSPF process was not able to pick any v4 version. And we know that router ID for BGP, EIGRP or OSPF, it's always v4 format. Okay, even if you're using a router with all v6, these router ID will be still a v4 format only. Okay, now let's configure it manually then, because we don't have v4 on any interface and these will not come up. So let's give some simple router ID. Okay, now the OSPF process will come up. So if I say do debug IP adjacency, we okay, debug IP OSPF adjacency, we can see the hello packets will be flowing out. Okay, the same thing I'll also do, I'll also configure the process here for OSPF. Let's say IPv6 router OSPF process ID is locally available. Okay, so we don't have to bother about the two things to be matched. Okay, so I configured process for OSPF, but it said that it's not gonna pick anything. So let's do it. Okay, let's configure it. So let's say, so what is the router ID here? So it's this. So over here, let me define something else. Okay, so one router ID 104, and over here this is a different router ID. Now what are the networks that we gonna advertise here? Okay, so let's configure the network. So let's say router IPv6, router OSPF1. Let's go with the interface command, or let's go with the global command. It doesn't matter, both are okay. Okay, so let's say on my interface E0/0, I'm gonna define my OSPF process IPv6 OSPF process ID 1 area 0. Same thing over here, the interface E0/0, I'm gonna say IPv6 OSPF 1 area 0. So let's see if we get something. Do show okay, so we have the adjacency coming up. There is no routes learned because we just have advertised our directly connected network. Okay, so let's also advertise the loopback now. So let's say loopback 1 IPv6 OSPF area or process ID area 0, and the same thing over here. Let's say Let's go to loopback first. Let's say IPv6 OSPF process ID 1 area 0. Now we can see the networks getting advertised or learnt here. IPv6 route OSPF. Okay, so we can see the loopback is getting advertised. Okay, the working is very similar, IPv4 and IPv6. It's little bit on the practice. Okay, if you can do some configuration, a simple configuration here, then that will work. Okay, how do we check the routing tables? Show IPv6 OSPF neighbors. If I want to see the database, this is the command which is gonna show me all the LSAs. If I want to see the routing table, I can make use of route OSPF. So this is my loopback address that's getting advertised. Okay, if I say show IPv6 route, okay, let's see how is this network learned. So it's learned over OSPF1. This is the distance, this is the metric. Intra stands for same area. Okay, might be you can try this on your side. Okay, now what I have done at present is I have considered all in area zeros. Okay, so this is area 0, this is area 0, and this is area 0. So basically it was pretty simple. Now you can try giving this as area 1 and you have 0, and then maybe you have area 10 or area 20. You can see the number of LSs, but as I told you, they are gonna be very similar to your v4. Okay, it's just about how you configure and little different in the command configuration or a command push. Okay, so if you see here, we made use of some different commands. We added up v6 every possible way. So routing table IPv6, neighbor table v6. Okay, also while configuring, we did some changes. Okay, now I want to show you something here. When I go to IPv6 router OSPF1, if I type network, okay, there is no such statement called as network. Let's do a question mark. We have router ID, which is a IPv4 format. There is no network statement. Okay, if there is no network statement, how do you think you will advertise your IPv6 network? IPv6 network in the OSPF process, right? So let me tell you, in the case of version 6, we don't have the global way of configuring OSPF. Okay, you need to go to the interface level and then only you can configure OSPF. Okay, even in IPv4, when I say that there are two ways: global way, which is you go to the router process and then you define OSPF, or you can go to the interface and then you can define. Okay, so basically these are called the traditional method or legacy method or very older method, whereas this is a latest method. Both will do the job if it is v4. Okay, in the case of global, what happens is it's gonna get activated on all the interfaces by default, but might be we don't need that. We need it to be more specific on interface. So let's say I need it on this. Instead of that, in a global would have activated on all the interfaces. If I would have made use of a broad statement called as network 000, now that activates on every interfaces. There will be hello packet getting processed, right? So that's a legacy method. So if you use interface method, you are more specific to what you need. In the case of IPv6, it don't let you give two different option. It's only gonna give you one option, that is to configure via interface method. Okay, fine. So that's about IPv6. This was just a basic from CCNA point of view. Okay, your CCNP doesn't even say that to discuss about all those things, but I thought if I don't discuss, if I don't disclose or discuss all these things, I don't think then that's beneficial for anyone, right? So the actual IPv6 portion for CCNP is this one, okay, which says about some security features like RA guard, DHCP guard, binding table, and ND inspection and source guard. Okay, and rest of IP6 is from the protocols, like we have V3, EIGRP V6, BGP V6. Okay, but basics were not being asked in this CCNP because basics are covered in the CCNA. So I thought first let's take with the basics and then we can start up with the new things. Okay, so give me 1 second, let me check few things here. Okay, so regarding this topics, okay, so let me make use of this prompt. So let's say IPv6 security features. Okay, we all aware of IPv4 so far. So IPv4 has those L2 securities. It supports port security, right? It's gonna have those DHCP snooping in the case of DHCP attacks. It has other prevention methods for every protocol. It has some mechanism to avoid that, right? So in the case of IPv6 also we do have certain things. We call them as first hop security features. Okay, now don't be confused with the term first hop. It doesn't mean that this is between ISP and the routers. Okay, it's not that way. It's going to be between the router to your switch and the switch that connects to the host. Okay, so over here we are gonna apply the IPv6 securities. What kind of securities? The terms like RA guard, which is also called as root advertisement guard. We have concepts like DHCP V6 guard. So as the name says, it's related to the DHCP snooping. We also have something called as ND inspection. Okay, and we have the last one as called as source guard. Okay, so these are all applicable in your layer 2. So basically don't think that these are like layer 3 capables. These are all from your end device, between end device to the router. So this path has to be secured, right? Now let's discuss one after one. So let's say in the case of RA guard, or also called as router advertisement. So in the case of IPv6, let's say if a host is configured to receive IPv6 data, okay, so host is not gonna see from where is it going to receive or who is going to send it. Okay, so basically anyone is sending some IPv6 data, the host is gonna adopt it. Now that can lead to some issue if someone is trying to send the DOS attack or multiple such packet. So host is gonna respond to each and every such packet, and we can be a victim of the DOS attack. Okay, so what we do is we put this kind of security called as router advertisement. So what the RA guard does is, RA guard will enable feature like filtering. Okay, or I can say that if let's say I put a ACL filtering, now what happens, those I have allowed will only be permitted to ping this or do a telnet or SSH. The rest will get declined or denied, right? Similar way, route advertisement is such feature where I'm gonna put some policy. I'm gonna say that if I get something from the source 1.1 or in terms of IPv6, if we get something from such a source, allow it. Our rest get denied. We don't want to use it. Okay. So basically, we can see the basics here. Let's say we can make use of policies to enable RA guard, or we can also adopt the simple ACLs without any complicated policies. So these are the two ways we can configure RA guard and we can get it going. Okay, so it's basis on the source incoming traffic. Regarding DHCP v6, so as we know that if I have a router, and let's say this is a switch, and switch is connected to a DHCP server. Okay, so the DORA process happens or should happen between the legitimate server, but for some reason there was a rogue DHCP server, and this rogue server is offering the IPs, right? So what we normally do is we put the DHCP snooping feature. We're gonna say that this is always trust. So if you receive something from here, then you adopt it, but the rest of the interface will be considered as untrust interfaces. And R1, if it is a host or if it is configured on DHCP, so they will not adopt any IP offering from any untrusted sources. Same concept for DHCP v6. Okay, we are gonna set something called as DHCP snooping in the case of IPv6 also. So the host or the server or the client, not server, the client is gonna take the IP addresses only from the trusted source and nothing else. Okay, and the last one here is IPv6 ND inspection. Okay, so basically ND inspection, or I can say that neighbor solicitation, NS, and neighbor advertisement, NA. So these are with respective to the IPv6 neighborship. Okay, so basically what this switch does is, we are all talking from the layer 2 point of view, layer 2 security. Okay, so what switch does is, it's gonna check the table for the neighbor bindings. Okay, it's gonna check for the neighbor bindings. If the bindings are happening or if the bindings are being set, the switch is gonna respond or forward those packets to upstreams or the host machine. But if the bindings are not present, the switch is just gonna drop that. Okay, like say for example, in the case of IPv4, if I set some MAC address with its IPv4 address, so those will be forwarded. Rest, if they are not binded up, so they will drop it. Okay, similar concept, we can just form the bindings and we can just deny other packets. Okay, so this ends your IPv6 topic. So let me know if you guys have any doubt here with respective to IPv6. and then I'm gonna take the SD-WAN topic. Okay, so that's very simple topic, might be 10-15 minutes for SD-WAN. So let me know if things are clear so far from IPv6 point of view. So let me unmute you guys if you wanna talk, or if you wanna tell something, or you wanna ask something. So if there is no doubt, then we'll continue with the SD-WAN.